Okay, so in the first part, we focused on the dynamical system, the hadron in QCD, and how we think about hadron structure in QCD. We now come to a different topic, which is electron scattering as a probe of hadron structure. So this will be more general and more experimental. It will be another short introduction then before we put these two things together and see what kind of hadron structure measurements we can do at the EIC. So I would propose that we go over this electron scattering kinematics perhaps a bit more quickly, because you may have heard some of this in Patricia's lecture, and also some of the concepts may be more familiar. But please feel free to interrupt at any time. So electron scattering. Let's first talk about the kinematic variables. This is a process where we think of like electron coming in, electron scattering from a hadron. The electron goes out and is detected, and the hadron does something. It can either recoil elastically, it can transition to a different hadronic state, it can break up into lots of other hadrons, etc. So this is very general here. And in leading order of the electromagnetic coupling, this interaction between the electron and the hadron happens through what is called virtual photon exchange, or more formally, this is what is probed here in the hadron is the transition matrix element of the electromagnetic current operator between the initial hadron state and the final hadron state. So in these processes, the particles are described by their 4 momenta. So the 0 component is the energy, and then the 3 momentum. And the 4 momentum transfer of the process is defined as the difference of the 4 momenta of the incoming and outgoing electron. And since we're dealing with inelastic scattering here, the energy and momentum transfer in the process are generally independent. As you know, in elastic scattering, the energy and momentum transfer are correlated by the condition of having exactly 1 mass in the final state. But here, this is inelastic scattering, so we have to think of the energy and the momentum transfer as 2 independent variables. Now, it is very convenient to work with relativistically invariant variables, which generally are defined as through scalar products of 4 vectors. This because, as we know from the theory of relativity, Lorentz invariance, these scalar products, the individual 4 vectors, their components change under Lorentz transformations, but the scalar products are invariant. So if we define variables as scalar products of 4 vectors, we automatically have them invariant or the same in any reference frame. And the variables one uses are the 4 momentum transfer. So this is the square of the 4 momentum transfer 4 vector. And usually, because the vector Q is a space-like vector, so its square is negative. And usually one defines a capital Q square, which has is minus the actual 4 momentum transfer Q square to have a positive number, just because for some reason people like to deal with positive numbers. And another invariant variable that we use is defined here. It's called it's of the type of a scaling variable, so it's a ratio of 2 invariants. In this case, this is the ratio of the 4 momentum transfer to the scalar product of the initial hadron momentum and the 4 momentum transfer Pn dot Q. So it's something like a ratio between the momentum transfer and the energy transfer in the process. And it literally acquires this meaning in the rest frame of the target. So this is the famous Bjorken scaling variable. And you will see that it's convenient to use such variables because they have a direct interpretation than when we think of the hadron structure in the parton picture. So when we think about our parton picture now of hadron structure, the way in which these kinematic variables define what we probe in the system is as follows. So the Bjorken scaling variable essentially selects the momentum fraction x of the parton we are probing in the system. This is a very basic fact. It just follows from energy momentum conservation. The momentum transfer Q sets the resolution scale at which we probe the system. So essentially, we can think of this 1 over Q as a kind of spatial resolution with which we probe the structure of the system, or conversely, we can think of Q itself as a kind of cutoff on the transverse momenta that we allow in the system when we probe it. So you see that there's a direct connection of the external kinematic variables, Q square and X Bjorken, with the internal variables in the parton picture. But of course, just as a side remark, we can use these variables in any, these are kinematic variables, they're objectively defined. We can use them in any context outside or even outside of the parton picture. They just happen to be very convenient when we work with the parton picture. So what is typically measured in electron scattering, or the primary observable, is the cross section. And in this example, we consider inclusive scattering, where we just measure the total cross section for this electron on the nucleon to go into any kind of final state without any distinction. And the cross section that is measured is typically presented in it's a differential cross section, differential in the kinematic variables, and it's typically presented as differentially in these invariant variables X Bjorken and Q square. And in this form, the cross section can be presented as some kinematic factor, which is essentially the flux of virtual photons emerging from this electron, times some so-called structure functions, which present the hadronic part of the cross section. They are functions of the kinematic variables X Bjorken and Q square, and these are completely like model-independent quantities. They just parameterize the cross section. They are as good as the cross section, so to speak. And now, so we can think of these structure functions as the primary object of the measurement, like what we can actually extract from experiment. Now, in the context of QCD factorization, as we saw earlier, in the context of the parton picture and of QCD factorization, we can express these structure functions in terms of the parton densities in the system. And this is presented here for the case of inclusive scattering. So the F1 structure function is given here by, as you see, some integral over x of the sum of quark and anti-quark distributions. This is where these are the up-down strange quark distributions. We sum over all the flavors. This is multiplied with the quark charge square, which describes the coupling of these quarks to the electromagnetic current. And also under the integral, we have some coefficient function CQ, which exactly accounts for the effect of, which accounts for two things: for the actual quark level scattering process and for the radiation that accompanies the scattering process that connects the structure at the scale mu square with the probe at the scale q square. So this is exactly what we discussed in the first part in factorization. So we present the structure of the target at some scale mu square, which we can choose of the order of the hadronic scale, and then we sum up all the radiation that induces transverse momenta between that scale mu square and the scale q square. This can be done in perturbation theory, and this goes into these so-called coefficient functions. And there's also a contribution of gluons to this electromagnetic scattering process, even though the gluons themselves carry no electric charge, but through this radiation process, they can couple to quark-antiquark pairs, and our electromagnetic current can couple to one of these quark-antiquark pairs. There is what we say, a coefficient function for the gluon density to contribute to the electromagnetic cross-section. So this is really like factorization in action. This is the end result of it. These kinds of formulas you will see in any kind of experimental analysis. And we can use these formulas in two ways. We can either predict the cross-section from a model of the parton densities, or we can do the reverse. We can extract the parton densities from the measured cross-section. And now here we presented this workflow for inclusive scattering, which is the simplest process. A very similar workflow governs semi-inclusive scattering, where we look for example, for some identified hadron in the final state, or even exclusive scattering, where our hadronic final state involves the original nucleon plus some meson or photon or so. So it's all variations on the same theme. All right, let's talk about polarization, which is one important element, in particular in measurements with the electron-ion collider. So we can do measurements where either the electron beam or the target, the nucleon target, or both are polarized. In some cases, one can also do measurements in which particles in the final state are polarized. Those are done at Jefferson Lab in fixed target scattering, but those we will not touch here. So we will have polarization in the initial state in the form of beam and target polarization. And exactly the same template can be, as we had on the previous slide, can be applied to polarized scattering. So now the basic observable is the typical spin difference of the differential cross-section, where we reverse, for example, the target spin or the beam spin, while the other one remains in the same spin state. The spin difference of the cross-section is parameterized by so-called spin structure functions. And then same story again, we can apply factorization now to the polarized cross-section. And it is expressed now in terms of as an integral over the what's called the polarized quark densities in the target, which describe the probability to find a quark with polarization along minus the probability with polarization opposite to the spin polarization of the nucleon. And same story again, there can even be a contribution from the polarized gluon density to polarized electromagnetic scattering. And just one comment so this is for the polarized differential cross section. Now, typically what one measures in the experiments is it may not be the actual cross section, but what's called a spin asymmetry, which is the difference, which is the ratio of the difference, the spin difference of the cross sections and the spin sum of the cross sections. So this is essentially dividing now the expression for the spin-dependent differential cross section here by the previous expression we had for the spin-independent one. And this is an alternative observable. It's experimentally simpler than the absolute cross section because, for example, things like factors related to the luminosity or experimental efficiency cancel, etc. So many of these measurements involving spin actually measure spin asymmetries rather than cross sections. All right, so let's talk about the range, the kinematic range of variables that is accessible in scattering experiments at a given incident energy. So now we have to look at how much energy actually is provided by the initial state of the system, so the electron neutron in the initial state. And this is described in a Lorentz invariant way by the invariant S, which is the square of the sum of the four momenta of the initial electron and neutron. And this, again, this is a Lorentz invariant variable. It's a square of a four vector, but it has a very simple interpretation in the center of mass frame of the electron-neutron scattering process, where the momenta of the particles are back to back. Namely, in the center of mass frame, this is simply the square of the total center of mass energy of the system. And now it's easy to figure out what the accessible range in X Bjorken and Q square is for scattering at a given center of mass energy. And it's given by this simple formula here. So for a given center of mass energy S and a given value of X Bjorken, the value of Q square is limited by this expression here, X Bjorken times S minus M square. So this is just kinematics. I mean, you can easily do this calculation yourself. It's a nice exercise with four vectors and scaling variables. So this means that in scattering at a given center of mass energy, the kinematic coverage looks as follows. It's a kind of in this plot here, which has X on the horizontal axis on the logarithmic scale and Q square on the vertical axis on the logarithmic scale. The kinematic coverage in a scattering experiment with given S is a kind of triangle that is to the lower right of this lines here, these lines represent the kinematic limit where where Q square reaches its maximum value. And you can see how the range available in X and Q square expands with increasing center of mass energy. So, for example, in measurements at JLab 12 GeV, which is a fixed target machine, we have this kinematic coverage indicated here. So we are limited to values of X that are larger than around 0.1, at least if we want to have some value of Q square that is above 1 GeV square. And then with the higher center of mass energies provided by the electron-ion collider, we open up a large new domain of X and Q square. We both go to smaller X, and we can also go to higher Q square. Now, just one comment here. This is the theoretical kinematic coverage. So in practice, there are other limitations that come from, for example, from deteriorating experimental resolution or so. So in practice, the kinematic coverage in these facilities is typically limited to some strip that covers maybe 1 or 2 orders of magnitude that is parallel to this diagonal line. So it's generally very difficult to measure, say, low Q square, high X in a high energy machine for various experimental reasons. So just be aware of this. This is the theoretical coverage I'm giving you here, and there are other limitations. So, yes.
I have a question. So for the previous plot, is there like a way to also have that plot and then as a function of the number of nucleons in an ion?
Yeah, very good point. We've discussed kinematics for electron-nucleon or electron-proton scattering here. For electron-ion scattering, these definitions have to be adjusted, even like what we mean by the Bjorken scaling variable has to be adjusted. So usually one defines the Bjorken scaling variable for scattering on an ion such that we divide by the mass number of the ion so that the values of X Bjorken are the same as they would be for a free nucleon if it with some small corrections for nuclear binding. Also, the center of what we mean by the center of mass energy has to be in electron-ion scattering has to be adjusted because we see that the total force momentum of the beam enters in S. So usually one defines the center of mass energy as per nucleon. So in all the, it's a good point. I should have commented on this here. In all the EIC plots, etc., you see when we talk about the square root of S, it's always for electron-nucleon scattering, where nucleon means a proton or neutron in the ion at the nominal momentum, which is ion momentum divided by nuclear mass number. Okay, very good. Let's briefly talk about the experimental setups in electron scattering, and this could be a whole conference in itself. So there are essentially 2 methods. One is to shoot a beam of electrons or muons, for that matter, on a fixed target, which can be in a solid, liquid, or gaseous state. In this way, one can usually achieve high luminosities just from the density of protons or nuclei in the target, or as we like to say, Comrade Avogadro works for you. You know, it's like you get Avogadro's number of particles in the target, and you get a huge boost in your rate. There are also technologies available for realizing polarized targets. You probably heard about some of them in Patricia's talk. But in this setup, the center of mass energy is given by this expression here, and you see it grows only linearly in the incident incident beam energy. So it's difficult to reach high center of mass energies in this setup. Now, another technology is colliding beams. Here, so this means we collide an electron beam with a proton or ion beam, and both beams are, let's say, have multi-GeV energies, are ultra-relativistic. So in this case, the center of mass energy grows as the product of the beam energies. And you see that gains us 1 power, and it's much easier to realize higher center of mass energies. this colliding beam setup also has a number of other advantages, which we'll summarize here. I mean, this is like terribly generalizing. I mean, there's lots of details and nuance about these technologies, which is not covered here. But generally, scattering between colliding beams can be done in a way that is very energy efficient. These beams are in storage rings, and they move around essentially like electromagnetic currents that go on forever. So the bunches in these currents can collide many times, and that's whereas in fixed target scattering, you shoot a beam at a target and you essentially dump it. So at some point it becomes very inefficient to say realize high energies and high intensities in fixed target. The colliding beam setup is also very clean for scattering processes, in the sense that there's no target material. You don't have target cells or so, which always do contribute to scattering. You have, very importantly, you have no scattering from atomic electrons, which is a big nuisance here for example, in large acceptance detectors here, like class 12. I mean, you have a solid target. It's surrounded by atomic electrons, and of course, our incoming electrons can scatter with these atomic electrons and create all kinds of. It creates some very intense radiation in certain parts of the detector. All this is avoided in colliding beam experiments. And also there's no dilution by other nuclei. So for example, many of the targets in fixed target experiments use some mixed, some molecules like ammonia or so, and you want to scatter from the hydrogen, but not from the nitrogen, and you need to make all kinds of corrections for that. In colliding beams, I say you deal with one species and it's fully stripped, and so it's a lot cleaner. The colliding beam experiments are also, they offer new opportunities for detection, because you can have the final state particles emerge at large angles, depending on the incoming center of mass energies. So imagine you do some high Q-square scattering, and then your electron and your recoiling hadronic system, they can actually emerge at large angles of the order of whatever 90 degrees in the detector. Whereas in fixed target, as you understand, everything is becomes very forward boosted at some point. Now, and another very interesting aspect of colliding beam experiments is you can do what is called far forward detection. That means you have, if you have particles in the proton or ion beam that receive only a small momentum transfer, for example, a nuclear remnant in a nuclear breakup process, or a proton in some exclusive process, these particles move along the outgoing ion beam direction, and they can be detected with so-called far forward detectors. That's a very interesting technology. And it's actually much easier to get these particles out detected than in fixed target, where slow particles are usually stuck in the target walls. Now, the colliding beam setup has some challenges. It's much more difficult to achieve high luminosity. This is terribly superficial, what I'm saying here. My colleagues in accelerator physics would regard this as as probably not very professional, but it requires beam quality. So the beam has to, the phase space occupied in position and momentum occupied by the beams needs to be small. This requires a technique, what's called cooling. It also requires some particular focusing of the beams. It requires some adjustments for the collision geometry or so. So there's a whole level of ingenuity required in getting high luminosity in a colliding beam experiment. And also what this requires is it really needs an integrated design of the interaction region where the beams collide, of the detector. Everything has to be fully integrated. It's quite different from fixed target experiments where, say, you can have a you can have a target and then you think what detectors you put around it to measure something. So, and at the social level, this also means that these collider experiments have a very different structure. These are large collaborations that are usually built around one central detector, because otherwise it couldn't be organized any other way. Now, now we come to another important quantity, which is luminosity. So luminosity determines the event rate you get with a certain setup with a given cross section. So it's a kind of aggregate quantity that accumulates all the experimental factors that go into what's the theoretical number of collisions per time that can be achieved, things like target density, beam current, all that. But it's a very crucial number. So because it directly determines the event rate. In particular, we need high luminosity, and I will quantify what high means in a second, for any of the following applications: for rare processes that have a small cross-section, for example, some exclusive scattering processes, very high PT hadrons, scattering on nuclei in some rare configurations. We also need high luminosities if we want to do multidimensional binning, because if our cross-section is differential in 4 or 5 variables, and we want to keep, and we want to have binning in all of them, we rapidly, we need a lot of statistics to have a meaningful event number in these multidimensional bins. This is an issue in particular in the measurements for transverse imaging, TMD evolution, and jets. We also need high luminosity for measuring spin asymmetries. We saw on the previous slide that what we measure is a spin difference of cross sections. Usually those spin differences are maybe like a few % of the total cross section. So we actually kill a lot of our statistics by taking the spin differences. And so luminosity is really very critical. Now, this figure here shows the existing and planned facilities in electron scattering and muon scattering distributed over center of mass energy, square root of S, and luminosity. Actually, I remember the first version of this plot was made by the chairman of our school, by Alberto, and then it was picked up by several other people. So the luminosity is measured in some funny units, which is per inverse square centimeters and inverse seconds. This is due to the fact that, as we said, it's some aggregate quantity that measures like target density, beam current, etc. The units here are you see it's 10 to the 34, 10 to the 35. This comes because it effectively is a number of the order of Avogadro's number. And what is more meaningful, or what will be more meaningful, will be actual event rates than that we see coming out of scattering processes at the EIC. But still, even with these weird units, you can do a comparison of the different facilities. And you see that at at a center of mass energy of around 5-6 GeV. We have, you see up here, the fixed target facilities that realize the absolute luminosity frontier, which is the Mainz microtron, the Bates Form Accelerated MIT and Jefferson Lab. They reach luminosities up to 10 to the 38 per square centimeter per second in these units. But they're limited in center of mass energy. Now down, what you see down here, Hermes and Compass, these are the spin physics experiments at CERN and at DESY and CERN. They use fixed target scattering, but at higher energies. With polarized targets, they achieve luminosities typically 10 to the 31 or 10 to the 32, which you see is like several orders of magnitude lower than Jefferson Lab. What you see down up here is the former Hera electron-proton collider, which was the first and only so far electron-proton collider, which had center of mass energies in the range between 200 and 300 GeV, but it was limited to luminosities of the order 10 to the 31. And the electron-ion collider that is being planned would sit in this region here. So center of mass energies from around 20 to 100 or maybe even 140 GeV, and luminosities going up to order of 10 to the 34 per square centimeter per second. So you see right away how this would push the combined energy and luminosity frontier in electromagnetic scattering, or more quantitatively, it would be 2 to 3 orders of magnitude higher in luminosity than the Hera collider that existed so far. So this just to put things in perspective. And now we can come back and connect this with our many-body system in the parton picture and see what kind of components of the system we can probe in different scattering experiments. So combining everything we saw about energy, the center of mass energies, and where our partons sit in X, we can make the following bold statement that in scattering experiments at Jefferson Lab with 12 GeV, we probe the valence quark component of this many-body system with the highest luminosity that is ever available and the greatest possible level of detail. With the EIC, we open up the region where both C quarks and gluons sit around X of 0.1, which are mainly due to non-perturbative interactions in the system, and also the vast region of X below 10 to the -2, where we have large numbers of gluons that are mostly due to radiation processes. So you can see that these two facilities are very complementary. And another thing we can do with the EIC is we can, as we say, all these structures depend on the resolution scale. And with the EIC, we obviously have a much wider range of Q² and can probe the system at different resolution scales. So for example, studies of the partonic structure at X around 0.1 as a function of Q², that will also be something that will become possible with the EIC. And again, as a reminder, before we go into the EIC experiments, this picture also summarizes what are the measurable properties of the system. These are the particle number densities, including their spin and flavor dependence, the transverse spatial distributions of the partons, the transverse orbital motion, including spin-orbit correlations, and even particle-particle correlations. And all these properties change with the resolution scale in a way that we developed earlier. And so this summarizes the part on electron scattering. We see that electron scattering probes partonic structure differentially in X, which is pretty much very closely correlated to X Bjorken, and in the scale mu square, with the variables X Bjorken and Q square, so to speak, directly related to the partonic variables X and mu square. We see that JLab 12GeV and EIC are complementary. JLab 12GeV probes partonic structure at X larger than 0.1, valence quarks at the highest luminosity. EIC probes structure mainly at X below 0.1 in the regions of C quarks and gluons, and can map out the scale dependence. And the luminosity is critical for many applications that we have seen. You had a question?
Yeah, I just had a question about like the nature of the events. So I'm assuming, is there a concept of like spectator nucleons when you have like an electron nucleon?
There is, and we will get to that in the nuclear part. I actually have an example on spectator detection.
Yeah, I just have so does that imply that there is, in the event geometry, there is a centrality definition?
That's a very good question. We can get to that after we've discussed spectator tagging. Short answer is by detecting spectators and using the information on about the nuclear configuration that comes from detecting the spectator, we can do an effective centrality trigger.
Okay, yeah. Thank you.
Okay, so now we're ready to put the two complexes together and look at actual scattering experiments, projections for scattering experiments at the EIC, and see both what they measure and what it contributes to the knowledge of the dynamical system in the parton picture. So in the following, we go over a few selected examples where this connection can be made very clear, but I can assure you that there are many more examples out there than can be covered here. So the first EIC measurement we want to discuss is the measurement of the polarization of the C quarks. As we said, that there are C quarks, anti-quarks, U bar, D bar, even strange quarks and anti-quarks in the neutron wave function, typically at X around 0.1 or smaller. A very interesting question is how these C quarks are polarized in a polarized nucleon. This is related to the question of what non-perturbative interactions create these C quarks, how they are connected to the valence quark component of the nucleon wave function. For example, are there mesonic degrees of freedom at work here? There's all kinds of hypotheses about what creates these C quarks. Now, these C quarks can be probed in using semi-inclusive scattering, where we detect a pion or a kaon from what's called the fragmentation of the struck quark. This allows us to effectively infer the charge and the flavor of the struck quark in the deep elastic scattering process. If we didn't do that, if we just did completely inclusive scattering, we couldn't tell whether we scatter from a U quark or a D quark or from a valence quark or a C quark. We would just measure the the aggregate effect. You can still get information about C quarks from inclusive scattering, but it's very limited. So it's much better to do semi-inclusive scattering, where we use the fact that the fragmentation process is very sensitive to the charge and the flavor of the quark. And here is, in these plots, is a summary of what we expect from EIC measurements. So the light blue band is what is presently known from, the red line is a current best fit. The light blue band is what we expect from EIC from inclusive measurements only, so not using this fragmentation information. And you see there's some constraints, but the uncertainties are very considerable. And then by using, using semi-inclusive scattering and the sensitivity to charge and flavor, we can narrow this down to the dark blue bands shown here. And you see that we can really map out in this way the X dependence of the anti-quark distributions in the nucleon, of the polarized anti-quark distributions in the nucleon. As I said, this can be interpreted in terms of hypotheses about the non-perturbative interactions that create these anti-quarks. And so I don't have time to go into details here. But this is just like one example of EIC measurements. And what we're using here in particular is the fact that the high energy of the collision ensures that the fragmentation of the struck quark happens independently from the evolution of the remnant of the target. This is such semi-inclusive measurements are also done at Jefferson Lab, but there the produced system and the target remnant are not very separate. And it's always a question to what extent this formalism is applicable here. With the, say, scattering energy of several tens of GeVs, we can really assume that this, jet that is produced evolves, it's in a very different rapidity region, and it really evolves separately from the target remnant.
Question here.
Yeah.
This might be a silly question, but why is the uncertainties, why are they flavor dependent? Like especially with the purple, where the center of mass, I believe that's like.
Mm-hmm. Oh, it's a good question for. It's because these analyses rely on a knowledge of the fragmentation functions, and the uncertainties depend on the flavor. So generally, because the U quark has a larger electric charge, or the charge square of the U quark is 4 times that of the D quark, we get much more information about U quark distributions from electromagnetic scattering. So the U quark tends to be better known, and the D quark, you have to do something to get it out. You have to do measurements on the neutron. So the uncertainties a priori are different, and including the uncertainties on the what's called the fragmentation functions of the quarks.
I'm assuming the uncertainty dependence in X is just because of the detector, like. Right?
The uncertainty dependence in X comes from 2 things. Both from the kinematic distribution of the pseudo data that were used in this, or were supposed in this analysis, and from the information flow in this what's called global analysis, which uses QCD evolution and actually correlates information at different X through QCD evolution, or in our language, through summing up the radiation.
Thank you.
Okay, very good. Now, let's move on to another very interesting measurement, which is often presented as like the flagship measurement of the EIC, which is the determination of gluon polarization in the nucleon. So here the basic question is, how are gluons in the partonic structure of the nucleon polarized? So the nucleon is now polarized longitudinally, as we say, along the motion of the partonic system, and we ask whether gluons are preferentially polarized along or opposite to that direction. Again, this is related to the question of non-perturbative interactions, which create these physical or transverse gluon modes from the valence quarks or from these non-perturbative vacuum fields. The question is also connected to what is the gluon contribution to the nucleon spin, and that is indirectly related to the question of how much orbital angular momentum is there in the nucleon wave function. We'll get to that on the next slide. So the gluon polarization can be extracted from electron-proton scattering. As we saw earlier, the electromagnetic current does not directly couple to the gluon because it doesn't carry charge, but the gluons couple to quark-antiquark pairs, which in turn couple to the electromagnetic current. And this means that the sensitivity or such quark-antiquark pairs are part of their creation is part of the radiation processes that are summed up in QCD factorization and that define the scale dependence. And actually, one can show directly that the gluon sensitivity to the inclusive of the inclusive cross section is directly related to the Q-square dependence of that cross section. So this gives us a handle to extract the gluon density by following the Q-square evolution of the inclusive cross section. Another method to get at the gluon density is to look at the production of a heavy quark pair in the final state. So if this is like a charm-anti-charm pair, then this can be detected through the fragmentation. So that's another channel that is being discussed for the EIC. Now, another alternative method to measure the polarized gluon distribution has been explored very extensively at RIC, which is polarized proton-proton collisions. And that's where our large part of our present knowledge of delta G comes from. Now, with the EIC, we can do a very nice measurement of the polarized gluon density by the results are shown in this figure here. So again, the light blue band is the present uncertainty on the polarized gluon density. You see that there's essentially no constraints below x around 10 to the minus 1. And with the EIC, we would be able to, just from these inclusive measurements and Q-square evolution, to do a very nice, very precise determination of the gluon density polarization. And here, we're in particular using the fact that the wide range of x and q square allows us to effectively extract the gluon density from inclusive scattering. So we need to follow these trajectories of the evolution equation ideally over several orders of magnitude in x and q square in order to get a good sensitivity to the gluons. Now, the measurement of the gluon density is related to some other very interesting topic in nucleon structure, which is the spin decomposition of the nucleon and the role of orbital angular momentum. And again, this could be subject of a whole lecture in itself. So there is in the context of the parton picture, there is a sum rule which states that the total spin of the nucleon in longitudinal polarization now can be decomposed or is made up of several terms. One is the polarization of quarks, and anti-quarks, which is called delta sigma here. The other is the spin polarization of gluons, which was the subject of the measurement on the previous slide. And other possible contributions come from the orbital angular momenta of quarks and gluons. So this is just one example of what's called a partonic sum rule. It follows from angular momentum conservation. And now the first two terms, the quark spin contribution and the gluon spin contribution, they can be extracted experimentally as the integrals over x of the polarized quark plus anti-quark distributions and the polarized gluon distribution. So, I mean, this spin sum rule has been discussed endlessly, almost too much, but it is a very important aspect of nucleon structure. And in particular, a determination of the gluon spin through EIC measurements would provide some constraint on the total amount of orbital angular momentum in the nucleon. And this is summarized in this figure here. I don't want to get into too much detail here, but essentially what is shown here is the rearranged sum rule, which is 1/2 minus what is known about delta sigma and delta G from present measurements. And then what you see here is the ellipses are what would be inferred from EIC measurements. And the lines here are indicative of the orbital angular momentum content that would be required to complement this sum rule. And so you see that at present, practically very little is known about the orbital angular momentum content in the nucleon. Certainly, we don't expect orbital angular momentum of whatever 5 or 10 h-bar in the system. So it's a bit the figure is a bit dramatized here, but you can see that as these measurements get more precise, we actually can make some inferences about the total amount of orbital angular momentum in the system. And this raises another very interesting question, which is what about direct demonstrations of partonic angular momentum? So can we see some observables that are directly proportional to the orbital angular momentum content in the wave function? And the answer is yes. This is possible through essentially two lines of measurements. One is a semi-inclusive transverse single spin asymmetries, and the other is so-called exclusive processes probing generalized parton distributions. And we'll see examples of these in the following. And I should say that orbital angular momentum is expected to be particularly large in the valence quark region, especially around x going to 1, and where it shows up in parton densities at large x in the nucleon form factors. And so the Jefferson Lab 12GeV measurements actually have a good shot at seeing orbital angular momentum at large x. But with the EIC, one place that we can really demonstrate orbital angular momentum is in what's called the azimuthal asymmetries in semi-inclusive, in polarized semi-inclusive electron scattering, because they are due to so-called spin-orbit interactions where the angular momentum of the partons enters directly. Now, again, this is a rather complex topic. This could be a whole lecture in itself. But let me just give you the essence of it. So here we look at some, we do like semi-inclusive production. So we look at some hadron that arises from the fragmentation of the struck quark. And we look at the azimuthal asymmetry or azimuthal angle dependence of the cross-section now, which is given by a structure indicated here. So this is the cross product of the transverse spin of the target with the transverse momentum of the observed hadron dotted into the vector of the longitudinal direction. You can see that this structure has the right quantum numbers. It has the right parity because the spin is a pseudo vector. The transverse momentum is a true vector. The cross product of a pseudo vector with a true vector is a true scalar. And so this is one of these structures that is allowed by parity in the cross section, and it makes exactly what we call an azimuthal asymmetry. And it's very interesting to think about how this azimuthal asymmetry comes about as a result of interactions in the system. One can show that it requires actually several things. It requires transverse polarization of the nucleon. It requires orbital angular momentum in the wave function of the system. And it requires also so-called final state interactions of the struck quark with the remnant of the target. This is because these final state interactions make a phase of the amplitude, and some imaginary part is, or some factor of I is required in order to have this structure here non-zero. So it's a very complex, intriguing, observable, and our colleagues working on, it's called TMD physics, can tell you more about it. And again, it tells us lots of things about what non-perturbative dynamics is at work in this system here. And with the EIC, we can do a very nice measurement of these azimuthal asymmetries in scattering on a transversely polarized proton. And we can determine the underlying quark distribution sensitive to the orbital angular momentum, which is known as the Sivers function. And again, here we're using the fact that the wide X and Q square range allows for a test of the reaction mechanism, disentangling all these factors and seeing the effects of QCD evolution. So I have two more examples here. If I could present them, then we could just wrap up. I think it would be very natural. Yeah. So another physical characteristic of the nucleon in the parton picture that we can probe is the transverse spatial distribution of the partons. This transverse spatial distribution, so here we think about these quarks and gluons as being at certain impact parameters from the center, from the transverse center of the system. One can show that this is a good concept in the relativistic context. And one can define densities of these partons both in the longitudinal momentum X and in the transverse position B. So they describe us how partons with a given longitudinal momentum fraction X are distributed in transverse space. And that's a very interesting quantity to look at because it defines really the size and the shape of the nucleon in QCD, now in the sense of this parton picture of this many-body system. And also these transverse spatial distributions change with X in a characteristic way. They also change with the nucleon polarization. They change with the quark and gluon spin. And so all this tells us about aspects of dynamics in the system in a certain way. Now, this transverse spatial distribution of partons can be measured in exclusive processes, the type indicated here, where in the final state we have now just the scattered electron, the nucleon itself, which recoils elastically, and some system that is produced like a meson or a photon. So this is a completely different final state compared to the exclusive processes we had before. This is more like measuring a form factor of the nucleon, but now with involving a process that produces an additional meson or photon. So at high Q square, one can suppose that this production process takes place in the interaction with a single quark or gluon in the wave function of the nucleon. And so what this process measures is essentially like the nucleon form factor for partons with a given momentum fraction x. So now in this reaction, the nucleon receives a transverse momentum transfer, which is small, which is of the order of like a few hundred MeV or 1 GeV, so of the order of the hadronic scale. And essentially what we're measuring is something like the form factor of partons with given longitudinal momentum x in the nucleon. Just like the electromagnetic form factors measure the transverse distribution of charge and magnetization, now we're measuring the transverse distribution of partons with a given x in the nucleon. And by taking the Fourier transform of this measured momentum transfer dependence here, we can get the parton densities as a function of the impact parameter. And there's a very nice method. We have channels at our disposal that are particularly sensitive to quarks and gluons. For example, production of a J psi, some heavy quarkonium like J psi or upsilon probes it is coupled to gluons in the nucleon, and it probes the gluonic generalized parton distribution. Processes like rho zero phi production probe a mix of gluons and singlet quarks. Processes such as deeply virtual Compton scattering, the production of a real photon probe, mainly quarks, but also gluons at next to leading order. So we have a whole like range of processes with which to separate quarks and gluons here. And I just show you this here. This is an example of a measurement of the transverse spatial distribution of gluons in the proton using exclusive J psi electroproduction at the EIC. So this is now coming back to what we said earlier. This is now one case where we really have to do differential measurements in X Bjorken, in Q square, and in the transfer, the momentum transfer to the nucleon. And so we really need the full statistic that comes from the high luminosity. And but as you can see, then doing the Fourier transform, we can really extract the transverse spatial distributions of gluons in the nucleon. And again, this is this is connected in a very interesting way with the dynamics in the system, because we see that the transverse spatial distribution is actually expected to grow as we go down in X. And this can be connected with several dynamical mechanisms. And again, like if you look at gluons at large X, these are the so-called valence-like gluons that are really closely connected with the valence quarks. They have their own spatial distribution, which is expected to be actually narrower than the spatial distribution of the valence quarks. If you go somewhat down in X, we expect to see the gluons in the pion cloud of the nucleon, or the gluons that arise in a similar way as the quark-antiquark pairs in the nucleon wave function. If you go even further down in X, there's a very interesting mechanism posited by which the gluonic size of the nucleon broadens due to a diffusion type dynamics. Namely, gluons which we observe at small x are decay products of gluons at larger x through successive emission processes. And these emission processes, they tend to broaden the distribution of gluons in transverse space. So again, as you see, we can really read this like a book, and we can connect the transverse distribution of partons measured at various x with very specific ideas about dynamics in the system. Last example I want to discuss here is about the neutron. So, so far, all the measurements we have shown here were on the proton in electron-proton scattering. We also want to measure the other nucleon, the neutron. That is in particular necessary to perform the flavor separation of the quark distribution. So to separate U and D quarks using isospin symmetry, essentially the D quark distribution in the neutron, in the proton is equal to the U quark distribution in the neutron. So it's very important to have that neutron information. Now, as you all know, the neutron is available only in scattering on nuclei. And this comes with all kinds of complications because there are corrections from the motion, the Fermi motion of the neutron in the nucleus. There are corrections from nuclear binding. There are corrections to the polarization, effective polarization of the neutron in the nucleus. So if the nucleus is polarized, the neutrons are polarized only to some degree. And so, now, the cleanest method we have for realizing scattering on the neutron is actually to scatter on a deuteron and detect the spectator proton. This is also known as spectator tagging. This detection of the spectator proton does two things for us. First, it identifies events with an active neutron where the electromagnetic scattering happened on the neutron. And it also effectively controls the nuclear configuration during the high energy process, because we measure the cross-section now as a function of the spectator momentum, and we can select configurations where, for example, the relative momentum of the proton-neutron system is small and they're relatively far apart, or we can select configurations where they are, the relative momentum is large, few hundred MeV, and they sit on, they are in a small size configuration, interact very strongly. So we can really, if you like, select types of nuclear configurations by using the information on the spectator momentum. And in particular, we can use this to go to configurations where the neutron is free by doing so-called on-shell extrapolation in the spectator momentum. This means doing analytic continuation to slightly unphysical values of the spectator momentum, so negative values of momentum square, where this neutron here in the deuteron is on mass shell and therefore behaves like a free neutron. It doesn't interact, it doesn't move, and so on. And so this is a very nice technique. I can provide further details during the discussion if you wish. And this can actually be done with the electron-ion collider. So we can measure the structure functions of the deuteron with spectator proton tagging, and then plot them as functions of the transverse momentum square of the spectator proton, and then take out some kinematic factors and really do the extrapolation into the unphysical region where this neutron is on mass shell and we get the free neutron. So it's a very beautiful example where we of using like analyticity in high energy scattering. This concludes the first part of this lecture. So let me just say we went over a few selected examples of EIC measurements. There are many other examples out there many other applications out there that are being pursued, and you should talk to our colleagues who care deeply about this or that or physics. So just a few of them that were not listed here. There will be studies of TMD evolution aimed at validating or testing the theory of QCD radiation in transverse momentum dependent observables, the transition from low to high PT. There's also a line of investigations using jets, QCD jets, as a probe of partonic structure, which is an extension of the semi-inclusive measurements presented here. There's a whole program on diffractive scattering on the proton, which aims to extract so-called diffractive parton densities, and in a certain sense can measure the quantum fluctuations of the gluon density in the proton as opposed to just its expectation value. There's a program of studies of pion-kaon structure involving peripheral scattering on the nucleon. There's also a whole program of electroweak charge current scattering for charge and flavor separation of quarks. And there's many more creative, in quotation mark, applications that people are pursuing. I will add a bibliography to these slides. I didn't get to that yet, but just for now, if you, the one reference I would recommend is the EIC yellow report, which is the most current authoritative statement of these projected measurements. So in summary, the EIC will answer basic questions about nucleon and hadron partonic structure in the region of C quarks and gluons. The partonic structure probed in high Q-square scattering processes can be directly connected with QCD effects on phenomena, both in the perturbative and non-perturbative domain. So we really learn about hadrons as emergent phenomena of QCD. And we need the need for the center of mass energy and luminosity of the EIC is evident in all the applications that were presented here. So this concludes the first part. Thank you for your patience. Thank you for allowing us to wrap up with this. And I'd be happy to take questions.
Right.
Perhaps I missed it, but in the proton tagging part, why is the on-shell momentum negative again?
It's because in the physical region, the neutron is never on mass shell. What's the easiest way to see this? So imagine the neutron were unbound or infinitesimally bound. The binding energy, the binding had a huge rate. Then in this case, the neutron 4 momentum would be equal to the sum of the nucleon 4 momenta. That would be, I mean, momenta are conserved in any case, but there would be no difference in the energies due to binding. Yeah. So now, when the neutron is bound, it means, in the sense of these 4 momentum variables, that the proton and the neutron cannot both be on mass shell. So it means in the physical region, which is positive momenta square, these guys are never on mass shell. We can go to a configuration like here where we detect the proton. So the proton is on mass shell, but then the neutron is off shell by some amount that is proportional to the binding energy. And in order to put the neutron also on mass shell, we can do that, yes, but we have to go to the unphysical region. And that means in these variables here, this means negative transverse momentum square.
For the proton then?
For the yeah.
Ah, okay. And then the neutron is positive because it's on shell.
Yeah.
Yeah, okay.
So you can, it's actually fun to work this out. You can define a momentum transfer T here between the deuteron and the proton. And then T minus nucleon mass square is exactly what's called the virtuality of the neutron. And you can express that virtuality in terms of the light cone variable, so the light cone momentum of the spectator proton and its transverse momentum, and you find that in the physical region, this virtuality is always non-zero, but if you go to negative transverse momentum squared, unphysical region, you can put it on shell. Yeah.
Yep, thank you.
Question.
So you described analyzing the hadron structures using a many-body system. So I'm familiar with that in terms of simulations, like in cosmology, simulating gases using many-body problems to like simulate galaxy structures. But I'm not sure how that plays into experimentalists.
Yeah, that's a very, very good question. So where's our many-body system? Yeah. So we projected this image of a wave function of the system, really in the sense of quantum mechanical coherence, as a kind of backdrop, and that allows us to visualize the system and discuss the place and the impact of these measurements. Now, in most simulation methods deal with probabilistic quantities. They cannot deal with quantum mechanical coherence, so they deal with actual particle densities. So people in high energy scattering, in some cases, use probabilistic Monte Carlos that have this picture in the background, but implemented somehow at the probabilistic level. Actual calculations of nucleon structure are usually not done in this picture. They're done using Euclidean correlation functions on the lattice. I mean, they can be interpreted in this way, but we are, as of now, the calculations we can actually do in this picture are very limited. We have no good way of dealing with quantum mechanical coherence in simulations. Right? There is, I should say this, there is one theoretical line of research. It's called light front quantization, where people actually try and construct these light front wave functions, but they it's so far most of the results are for some simple models where you can do this. The complications of doing this in the actual gauge theory of QCD are very significant, because you have to do then renormalization consistently within that framework, and you break certain symmetries, you break rotational symmetry. So that, but I'm just saying that there is a line of research that takes this wave function seriously and tries to actually use it for computation, but it's what has come out so far is very limited for QCD proper. Yeah.
Okay, thank you.
More questions?
Yeah, I just have maybe like not a question, but more like as a hunch. When it comes to gluon dominated, the gluon dominant regime,
yeah.
Does it tie to the initial state of the quark gluon plasma?
In short answer, yes. So when we get to nuclei in the next lecture, there is this kind of gluon-rich component of the nuclear wave function can figure as an initial condition for the quark gluon plasma. But that depends on, of course, other assumptions about what goes on in these collisions. But yes, I mean, people. There's a theoretical school. It's called the color glass condensate or so. They actually they have a certain set of approximations that allows them to compute this component of the wave function involving a large number of gluon at small x in some systematic way, essentially treating the rest of the nucleus as a set of color charges at large x, and then it's a kind of class action description of all the rest of the nucleus. And they actually use this concept of the partonic wave function. They calculate the wave function in the region where it has a large number of small x gluons, and they use it to model initial conditions in heavy ion collisions. So that thing is going on.
I guess does that in any way tie into like comparing like the initial condition, like the entropy for the initial condition and the final state? And
short answer, I'm sure it does, but I can't answer that question.
I'm just curious because at very low x, you just have a gluon dominated regime, and you can write a transfer matrix for that, and you can like calculate.
So indeed, people apply the concept of entropy, of thermodynamic entropy, to high energy collisions where large numbers of particles are being produced, and they I can't really comment on that in detail. In detail, I would need to prepare a bit.
Please, more questions.
Thank you for the talk. So my question is about factorization. So the calculation for factorization, is it exact or are there some assumptions behind it? And the second part to it is, does factorization hold at all orders in perturbation theory, or is it like up to a certain order? Like, is it true at an order or all?
These are both very good questions, and the second question is actually related to the first one. So the answer to the first question, the factorization is an approximation based on some putative asymptotic situation. So we have the hadronic scale, like typical inverse hadronic size, typical transverse momenta in the hadron. And we have the scale of our probe Q square, which is assumed to be much larger than the hadronic scale. So in factorization, we suppose that there's an asymptotic situation. We consider the formal asymptotic limit, Q square going to infinity, and we compute the leading terms in an asymptotic expansion generally in this hadronic scale divided square divided by Q square. Now, how so far at this level, this is a systematic expansion. So one using methods like operator product expansion or the method of regions in integrals, and so one can ascertain that the leading asymptotic contribution comes from certain types of trajectories in the transition amplitude, which we can compute in this factorized way. Now, how effective this asymptotic expansion is for real life situations, that's a practical question. So it can be that a term which is formally leading in mu square over Q square has and is calculable exactly. It could be that such a term is numerically small compared to some term that is formally down in 1 over Q square, but numerically large for all practical purposes. So that question has to be discussed case by case. And we see many applications of factorization where I would say the practical applicability is not as we would wish. Yeah, we compute some term that is leading in the formal power expansion, but it plays no role in practice. There are other cases where it works very well. So but it's always based on some asymptotics, really. And if you like the mathematical terms, it's really like asymptotic series. You compute an asymptotic series of a function, and then you use that asymptotic series for actual approximations.
And I have another question relating to structure functions. So when you showed the factorization for the structure functions, so structure function is independent of the scale, whereas the PDFs and the other term that was in it was scale dependent. So yeah, so the coefficient C and the PDF for Q and Q bar are scale dependent, whereas on the LHS it's scale independent, right?
Exactly.
So yeah, is there a way to visualize it, like not so mathematically, of how the scale dependence goes away?
It's a very good question. The scale dependence goes away because the scale dependence of in this way of writing the formula, the scale dependence of the parton density and the scale dependence of this function C, they are exactly the same. They're described by the same evolution equation. So you could, I mean, this is a particular way of writing it schematically. You could do it in a way that we split up this function C into two factors. One is a coefficient function depending only on Q square, and the other is some evolution factor that depends on Q square over mu square. And then you could attribute this evolution factor either to the parton density or to the coefficient function. So it's but what you say is absolutely correct. The structure function is essentially the cross section is observable. It does not depend on the scale. The scale is an artifact that comes in because we do this description, this factorized description, and we have to limit the transverse momentum content of our hadrons somewhere. But we know that whatever is not included in this wave function will be added then up by radiation. And but the total effect of this radiation is such that the cross section does not depend on the scale. So yeah, this is a very compact way of writing it. One could write it in a more I said if you wanted to emphasize evolution, which will be the subject of Nobuo Sato's lecture, then you would probably write it, as I said, in a way that we break this up into two factors, and then this evolution factor depends on explicitly on Q square over mu square, and it bridges the gap between the scale mu square and the scale Q square, and it can be attributed to either the parton density or the coefficient function, but the overall mu square dependence drops out.
Thank you.
Questions?
We will have more time tomorrow. We can come back to if you have any questions about the material that was presented today. I'd be happy to go over it tomorrow.
Yeah, just because they need not to be shy too. Anyways, we'll see next tomorrow.